Welcome again to the AMATYC 2013 webinar series, Using Mapping Diagrams to Understand Functions, with Professor Martin Flashman, and this presentation is sponsored by the Innovative Teaching and Learning Committee of AMATYC. AMATYC is the American Mathematical Association of two-year colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, you can visit our website at amatyc.org. So please note that the views expressed by the presenter are not necessarily the views of AMATYC, and any commercial products mentioned by the presenters are not endorsed by AMATYC. So now we're going to actually switch to the presenter slides, but Professor Flashman is actually going to just share his screen today, so I'm going to do a screen share to him. And as soon as he accepts that, his screen will start showing, and in about half an hour or so I will chime in with a link to the survey and how to get a certificate for attending today's webinar if your college requires that for professional development purposes. So if you could welcome Professor Flashman in the chat room, that would be greatly appreciated, and I'm going to turn my mic off and turn it over to him right now.
Well, thanks very much, John. I am really so sorry about the confusion here, but let's just get rolling with it, because I hope you're all interested in learning about using mapping diagrams to understand functions.
Martin, I think you muted your mic, so if you could unmute your mic, that would be helpful, because I see a cross through your mic, so that means that you muted it by...
There we go. Sorry, has anybody heard me? Okay, so again, boy, this is technically one of my worst days. First question is hands up or down. First question, are you familiar with mapping diagrams at all? How many people here are familiar with them? Lots of yeses, and okay. Lots of yeses. Okay, so of everybody there, we've got about 5 or 6. Well, okay, so I'm going to skip the next two because it doesn't look like there's a lot that are familiar with it, and we'll just go on to the next slide, which is about mapping diagrams. They're also called function diagrams and dynagraphs. So here's an example of a mapping diagram that has actually two functions. One function gives you the day of Thanksgiving, and the other gives you the day of Hanukkah. And in 2012, we had different days for Hanukkah and Thanksgiving, but in 2013, they're the same day, so we get that thanks Hanukkah. And here's another picture of some mapping diagrams that we'll maybe review at the end, but this will illustrate some of the ideas here. So we have a function, it's 2x minus 1 squared plus 3. I'm going to think about that as built up in steps as a composition. So first I have x minus 1, so I subtract 1. That's what this first part of the diagram does. Then the next thing is to square the result. So you see squaring going on here. So an input here of 0 gave an input of 0, input of 1 gave an input of 1, input of minus 1 also gave an input of minus 1, and an input of 2 gave an input of 4. We see that also for minus 2. And then finally, we have another linear thing, multiply by 2 and add 3, which is evidenced by this last part of the diagram. So we're going to be looking at mapping diagrams and see how they work and understanding functions. We're going to mainly focus on linear functions. I want to give you a little background on the history of this thing. And it goes back quite a while, actually, to the 19th century. But a recent, not so recent, 1971 book by Howard Swan and John Johnson was a fun source for visualizing functions and shows the connection between the mapping diagrams and the graph in this little excerpt here. This is his introduction to the arrows going from the domain to the range, and here's a picture of it in the first frame. Here's Professor McSquared, and here's some numbers in the domain, and they're being sent over here to values in the range, or the target as I call it, and then he sort of rearranges the whole thing and shows you how it might look on a graph when you eventually put the corner points in there and just leave the points and forget about the arrows. And then we get the kind of graph that you're more familiar with. So he also had, in this book, he had some exercises with mapping domains and ranges and little charts here, and also some figures to show how that corresponds from a mapping diagram to a graph. And if you are familiar at all with Michael Spivak's calculus book, which is sort of a classic of the more rigorous calculus books in existence, here's a figure from chapter 5 where Spivak is talking about, it looks like his functions are going from the bottom up here to show you a constant function, but on the bottom, they're also going from the bottom up, and they're showing you a cubic function. So those are the two examples from sort of a little bit older history. Now for the rest of the webinar, I'm going to be using some of the materials from thing I'm working on right now, which is mapping diagrams from A to C and D, and E, reference and resource book that I'm working on for visualizing functions. And this is preliminary sections that I'll be using that are not yet for publication, but if you want to copy this link, you can actually go to that link and see it yourself. I'm going to just open it up, I hope. And here it is. This is the overview page from the book, and this is a list here I have of links that to other things that are in the book. I'll show this later in the webinar, but let's just jump right into this visualizing functions. There's 4 usual ways that people understand functions. There's tables, algebraic equations, Cartesian coordinates, and this 4th method of the mapping diagram. And seems to open up again. Okay, okay. Keep opening me up here. I think they're opening up in my screen. Okay. Well, so here's a definition of a mapping diagram. It's a figure that has 2 lines, a left hand and a right hand. One I call the source or the domain, and the other I call the target or the codomain or the output and inputs, these things. And an arrow going from a point in the domain to the point in the target, which represents that the value at the number a when put into the function comes out with the value f of a visualized in the source. And the conventions are usually, I'm going to do them vertically. Some people do them horizontally, and later on maybe you'll see why I do them vertically when we think about how this is visualized. By the way, this technique is, these things are called nulls, which I got from Rob Beezer in his linear algebra book. Okay, so here's connecting mapping diagrams to graphs. And let's see if this will open up for us. And this is using GeoGebra. So here's a point in the plane, and there's a red line that corresponds to that point. So as I move that point in the plane, we see the arrow in a corresponding position. And over here we have a mapping diagram, an arrow in the mapping diagram, and we can see that corresponding to the point here as I move the first coordinate moves left and right. If I move the second coordinate, it moves up and down. And this is an easy way to see relationships between the things. And one other feature I'll point out here is I'll put in the arrows that actually show the connection from the input to the output here in the y-axis. So this is a connection that's very tight in the geometry of the Cartesian plane, that one point represents two pieces of data. And for students, that can be, in the transition to learning about functions, a piece where they get lost in the connection, and pretty soon they're not thinking about the functions as input and output. They're thinking about the graphs of the functions as holistic things, which is great, except it's very difficult to see some of the functional concepts with the graphs. So we're going to look at that some more. I'm going to close this up here. Actually, yeah, just move down here. And here's the first example showing all three ways to represent things. And we see here a table with the x values, the value of a linear function here, and then on the right we see the graph of that and the mapping figure. Now I'm going to go back here to our linear mapping diagram. Go back here to our resource here. And looking at linear functions, I've put here a worksheet that you can download at your convenience. The link for this is here. And this worksheet you can use in a classroom. Here's what it looks like. And you see I've given the students just some numbers to play with for t and f of t. There's no algebraic formula. And then I asked them to draw the arrows on the diagram and then put the corresponding points on the graph here for the students to see the correspondence between what's happening in the mapping diagram and what's happening on a graph. I also give them, similar to the one we have on the example there, I give them a linear function to play with, and they fill in the table, and then they complete the mapping diagram and the graph as well. Going back to the example here, here's what it looks like. Here's a table. You fill in the table pretty easily. And you can ask a question. Well, when is f of 0 equal? What is f of 0? That's pretty easy. That's minus 7. And for which x is f of x greater than 0? Well, it looks like x bigger than 1, but which x bigger than 1, we'll need a little bit more work on that. All right, here's how they start plotting the points on the graph. They plot some points, and then they might connect up the line and see how those points correspond to the graph line. Now, when we're doing this on the mapping diagram, let me put a pen here. So we might start off and put, say, 0 here, pretty big 0, and then put minus 7 somewhere on the chart here, minus 7, and then we draw an arrow from very sophisticated looking arrow. And then for 1, I'll put 1 up here. And once I put that 1 up there, that's really established the linear scale for the x-axis. And I'm going to send that to minus 2. Well, I don't know where minus 2 is, but once I put minus 2 in here, that establishes the scales for the target axis. And now we have the start of our mapping diagram. And if we want to know when's it going to be 0, we could go up one more unit here, 2, and see that at 2 it's 3. Well, that's going to be up 5 units here, so maybe that's the same distance up here as 5. That's 3. And draw that arrow. And now you might ask, well, how are we going to find out when it's 0, which is somewhere around here? And we'll get back to that later as to what value in the domain is going to get sent to 0. It's not going to be 1.5, but it will be somewhere in between there. Okay. So that's there's a much better looking picture of what's happening here, and we still have a problem with what value is actually 0, because here's 0 over here. Those scales are the same in this picture. Okay, so I want to look at a couple of different ways that people can draw these mapping diagrams using technology. And so let's go back to this page here and look at a couple of ways that we can draw these using technology. So first of all, there's you can draw these with spreadsheets. You make a spreadsheet maybe using Excel. I think you can download this spreadsheet. I'm going to see if it'll download here for a second. But in the spreadsheet, close that up. So in the spreadsheet, I have this is my cells, and they've all been created here. And then you see I have two diagrams. One looks like the graph, and here's the mapping diagram. And the really neat thing is that to change, to build a mapping diagram or a graph from a spreadsheet, all you need to do is insert a scatter plot. Well, that's pretty easy. You may be familiar with that. And just put in something like this. And there's a scatter plot. But here's what you do. On the scatter plot, you switch the row and column. And when you switch the row and the column up here in this feature here, the scatter plot turns into a mapping diagram. And that's something that's a well-hidden feature of most spreadsheets. And I hope that that in itself is worth the webinar that you get this information about how to build these things. They come built in on spreadsheets. You just have to change from going from the columns to the rows, and you get this really neat mapping diagram. And it shows you the features as the x's are going from -5 up to 5. The outputs are going from -7 up until 13. Very nice feature of spreadsheets, not known to many people. Okay, so that's how you can do it with spreadsheets. That's how I drew those figures. I sometimes, in the past month or two, have been learning how to use Sage, which is a really nice free online resource which does a lot of stuff like Mathematica. And here's a visualization using Sage, and you can go to this site to do this again, that makes the table, 2x plus 3, draws the graph, and here's the mapping diagram drawn automatically for you using Sage. And the last one I want to show you here is with GeoGebra. GeoGebra, I think, is really a wonderful tool now for doing all kinds of things. And here is a GeoGebra setup that I've built on the page. And you can see as I grab this marker that it puts out on the mapping diagram. Let's make that a little bit bigger. Well, we'll leave it there for now. Makes the mapping diagram. It also puts the points on the graph, and it corresponds to the points on the spreadsheet. All these features are available with GeoGebra. You can build these mapping diagrams pretty easily, or download them from this page I've given you and look at the as well. Also, I want to look a little bit at these things a little bit more dynamically, just to show you how this can help your students. So here's a GeoGebra that has a built-in animation showing you the mapping diagram as it moves along and comes back up. And a diagram like this, you can also grab the point and move it up and down yourself. And you can also put a trace on this if you like, and that will show you, if you move up, you can see how it looks by tracing it with moving your up and down arrow after you click on that one point and trace that whole thing. So that's a really nice feature using the animation. You can also, there are sliders. I have a slider example here. Here's a slider where it moves up with a slider, and again you can use the slider to move up and down. And finally, I have an example here where you just grab the object itself and move it up and down like this. Now, one of the features in each one of these, you might notice that the function is actually changeable. So GeoGebra, what I built here allows you to change the function. So instead of having 2x plus 3, I'm just going to change it right here rather than wait till later and make it minus 2x plus 3 and see what that does to the diagram. Well, we know what happens to the graph of the function. It's now going downhill, but here's what happens with the diagram. As the values of a go up, the value of the function go down. So we have this really nice visualization of that. And if I put a trace on the point here and move it, you see a rather nice feature, which is really kind of remarkable, especially when your students discover this on their own. And that is that all these arrows on the mapping diagram pass through one single point, the same point. And now we're going to turn our attention back to the slides here. Maybe I'll get to the slides. Here we are. And we'll look at some examples of what happens in the mapping diagrams. We know that the numbers, if we think about very simple core linear functions, and we're going to focus on linear functions now because they are, the core, the simplest functions that students encounter at the beginning of learning about functions, and basic concepts that you're going to use in functions all along can be learned and started on in the linear function. So that's where I'm going to start, and that's probably where we'll get to in the examples here. So let's look now at adding a constant and multiplying by a constant and see how they affect the mapping diagram. So the usual interpretation of m is a slope or a rate, or it's a magnification factor. And when m is positive, the function is increasing. When it's 0, it's a constant function. And when it's negative, it's a decreasing function. So here's some simple examples. We don't have time. There is a worksheet online for you to work on these, but since we've lost a lot of time, I'm just going to go to the solutions of these. And you might look at these and say, well, of all these, which one of these will have crossing arrows? And I think we've already guessed that it'll have a crossing arrow when it's -2. And at 0 is an interesting thing. We'll look at that in a second. So here's the -2 mapping diagram. And there's a point here where they all pass through, and I'll call that the focus point. And I label it with -2, 1 indicating the slope and the intercept. Here's slope 2, m is 2, and you see there's a magnification happening here. Here's the scale here, and back here in the background is the actual focus point. It happens before we get to the domain line, and if you think about the geometry of that, you can see why you might think of that m as a magnification factor. Okay, that focus point determines the value of the function. Once I choose a point on the axis here, then if I draw the line from that focus point through that wasn't too well drawn, that determines the value, and for a change of 2, I should be going up much higher in this thing. So that wasn't very well drawn. Let's erase that one and move on to the next slide. Here's a slope of a half. Now, if you slope of a half, you're magnifying, you're really shrinking, so you see the focus point is on the other side of the axis as the values, the intervals here are being shrunk by a factor of 1/2. Again, this point determines the values for all the other points because it's a linear function. Notice the value of b at 0, the value is 1. That's the value of b. So if you put in a 1, you get out a 0. You put in a 0, you get out a 1, and that's what the b means in the mapping diagram. Here's an interesting one that students have a lot of trouble with in graphing, because we know that the graph of the constant function f of x equals 1 is going to be a horizontal line. But that's, you think, well, gee, that line, the points in that line are moving. The points in the line are different, but the point in the target is the same. This is a really great way to think about a constant function. And I usually think about the domain as time, not too well drawn there. And over here is position going up or down, and so as time goes forward, this position is staying the same. It's a constant position. And that's how that's visualized in the mapping diagram. And finally, the trickiest one of all is x, and where the slope is 1. And that's tricky because the focus point here is not apparent on the graph. All the arrows are parallel to each other. And that's because, if you think about it a little bit, that point where they all meet is out at infinity. And that can be infinity out to the left or infinity to the right, but they are meeting way out here at infinity. Okay, so that's how the slope affects, or the magnification factor affects the diagram, and these are very important things. Here's a couple of problems that using these mapping diagrams can help with. So I'm going to try and solve these rather quickly using the mapping diagram. So the first one is, we'll just look at this one first. I want to solve the linear equation 2x plus 1 equals 5. Okay, so what I think about is, this is a function. The function is 2x plus 1. All right, so I'll put in at 0, the value is 1. And at 1, the value is 3. Put a 0 here. 2, 3. And so here's this line. Here's this line. And so we draw them back, and they meet at a point. That's our focus point. And we want to know when we're going to hit 5, for 5 up here. So we draw this line from 5 back to the focus point, and there's where it's going to hit, which looks like, well, it should be 2. My picture isn't too well drawn, but let's make believe it is. And see that that's how I found the solution to that equation. I had that visualized. When will the value be 5? The input will be 2. I'm going to move on here. Let's look at a fixed point here for this one, though. That would be, when will the arrow go straight across? So you take the focus point and you go straight across, and that will be a point where the value will be the same. And I think that's actually pretty accurately shown here as minus 1. If you use 2x plus 1, you put in minus 1. That's 2 times minus 1 plus 1. That's going to be minus 1, and that'll be your fixed point at minus 1. So you just have to find the focus, draw a horizontal line straight across, and find the point that will be left fixed. Okay, so let's look a little bit at composition, which is another great place for using mapping diagrams. And for this, I'm going to go again back to my website and back up here and open up the page that I have, these 2 pages on linear functions. And we'll look at the composition feature here. So here's composition, and here's an example of composition. And I have, this is with Sage, and I'm just going to evaluate that composition for Sage. And we'll see, there's the 2 functions. F is 2x minus 1, g is 3x plus 2, and there's the composition. You're seeing that with a step of 2. If you want to see which is, F is the red and g is the green, so I'm doing 3x plus 2, then 2x minus 1 applied to that. And if we want to see how that would work if I had a negative thing, I'll just change that, hit the enter, and that's what it looks like for a negative. So we can see the F is negative, we can see the crossing lines there, and the composition will also be crossing, and the blue lines represent the composition here in this diagram. Well, it's a little bit tight in that. Here's what it looks like with a very important example. Because every linear function can be thought of as a composition, and this is very important later on for thinking about inverses. So if the function is mx plus b, you can think about first multiply by m, then add b. So it is a composition. And we can see that here in this function. We have 3x plus 2. So first we multiply by 3. You can see that expanding over here. And then we add 2. That's over here. And we see the final graph in the blue, the mapping diagram in the blue. Here's what the graph looks like. And you may recall that it's really hard to see compositions in the graph of a function, but this is what the component functions look like here in thinking about it. First multiply by 3, that's the green line, and then add 2, that's the shift up, giving us the blue line. Again, I think it's a lot easier to understand this, the composition, with the mapping diagrams. I have one here in GeoGebra as well, but I'm going to look down here as well and now talk a little bit about the key concepts about thinking about inverses. So we know that inverses undo what the function does. So here's an example. Okay, let's reload this page. Sometimes Sage gets a little bit fussy about you using it too much. So here's an example with Sage. And this is, I think, a terrific picture to show you why these two functions, f and g, are inverses. You start off with g minus a half x plus a half, that's the green. You follow it with minus 2x plus 1, that's the blue, and your inputs end up being the same as your outputs in the composition. So this is a really beautiful way, I think, to understand how to check that you have the correct inverse function with a mapping diagram. Here's another one. This is one for the constant multiplication. Again, this is rather simple. We are taking a third of x, then multiplying it by 3 to get back to the identity. Now,
I'm going to interrupt and just say that you only have about a minute or two left, so if you'd like to make some concluding comments, and then I will let people know where the survey link is at, and then if you wouldn't mind staying to answer a few questions, that would be great.
No, I'd be happy to do that. I again apologize for the late start that we had, and I know people have other things to do. I wanted to point out one feature about the inverse for functions, which is that if you think about every linear function is a composition, first multiply, then add, then if you think about how to create the inverse, you just undo what you just did. So instead of adding, you subtract. Instead of multiplying, you divide. So you don't have to solve equations and switch variables. You just have to think about it functionally and reverse the order, which some people refer to as socks and shoes. You put on your socks, then you put on your shoes. If you want to undo that, first you take off your shoes, then you take off your socks. It's the same thing for linear functions. And here's an example of that. I'm going to let it go. Here's an example of that with GeoGebra. And I want to thank everybody for coming today. And if you're interested in more of these in the future, here's a function which is not the inverse, but it looks like it is. But when we move it, we see it's not the inverse. But if I change it, I can change that to, I'm supposed to subtract 2 from the number, and then divide by 3. So that's what I think will be the correct answer. And now you see that that's correct, and I can actually show that they're the same. And over here is the way it looks on a typical graph with this reflection principle showing up here, whereas in the mapping diagram, the reflection is just what arrow went up, it comes back down to where it was. That's the reflection principle for mapping diagrams. Thanks again, and I wish you a lot of luck in using these things. If you look on this page in the future, you'll be able to find the other features of mapping diagrams in my web page.
Okay. I don't know what, you must have closed the slides by
I
accident,
didn't close.
Martin, because I don't see them behind the.
I didn't close anything, but maybe.
Oh boy. Okay. Yes, I think it probably was an accident because unfortunately I don't see the slides anymore with the link up here. Okay, let me try
Oh, I don't know.
to.
Have I dropped off?
No,
I
you
don't know
have
if I
not,
dropped.
and that is because I didn't realize that the slides were no longer on the screen. So
Yeah, I saw the whole screen disappear a second ago, but it wasn't me.
let's see. Okay.
Okay, I'm back to sharing it. Okay, so here we go.
Oh, here. I'm sorry about that. It for some reason wasn't coming up in the spot that it normally
So,
was. So
all right, so the link you can send it out to this mapping diagrams from A to C and D. That link eventually, as the year goes, as the term goes on, there'll be more things on that link. Uh, not just visualize functions and the linear functions that I've talked about today, but all the rest of these topics will be eventually have real full, rich um, features with mapping diagrams for calculus and differential equations and trig
okay.
functions and exponentials.
Well,
Everything will
thank
be
you,
up there.
Martin. And let me just say that I know that some of you have to go right away, so if you could thank Martin again in the chat, that would be great. And so thanks again to all of you for participating in today's AMATYC webinar. And if you'd like to support future AMATYC webinars, please consider becoming a member of AMATYC, which I think all of you are. So you can do that at bit.ly/join-amatic. And remember to like us on Facebook at facebook.com/amatic. And recording of past AMATYC webinars can be found at bit.ly/amatic-webinars. And it usually takes us 1 to 2 weeks to get the webinars up to our archive. But we are going to actually try to rearrange them by topic in the future so that will be easier for you to find. And please take 2 minutes to complete our survey at bit.ly/amatic13, and this will also give you the spot to enter your email address if you need a certificate for participation in today's webinar. So let's thank Martin again, and Martin will again be more than welcome to stay and answer your questions. But this does end our webinar today.